So we were just talking about the difference between delta G standard and delta G. And just to recap, we said we had a reactant A going to a product B, and we saw that the standard change in Gibbs energy is the standard energy of B per mole minus the standard energy of A, and that delta G, we could say, was the chemical potential of B minus the chemical potential of A. So now we have to ask, is there some relationship between delta G standard and delta G for a reaction? And another way of saying that is to look at the right-hand sides of these two reactions. And so we look at this reaction, or the right-hand side of this equation, and the right-hand side of this equation, and say, is there any relationship between this and this? And we know the answer, right? We'll do that on the next slide. So we know that the standard Gibbs energy for a particular component, we could say, is the Gibbs energy per mole, and that is the same as the change in the Gibbs energy when we add a mole of A to a system, and of course that is just the chemical potential of A standard because we're talking about pure stuff. And we can say the same thing about B, right? That the chemical potential of B pure, let's go ahead and say pure B, is the standard chemical potential. And that allows us to then say, okay, we said that delta G of a reaction was equal to the chemical potential of B minus the chemical potential of A, and then we can plug in the equation for chemical potential, right? We said chemical potential as a function of composition is going to be the pure chemical potential plus RT log of the activity of B. And that allows us to say that this will be general, right? We can use this expression for real solutions as well as ideal solutions. And we can do the same thing for A. A. We can say chemical potential of A is the standard chemical potential plus RT log activity of A. And this doesn't need to be here. I don't know what that is. Let's erase it. Okay. Let's put a parenthesis on there. So so basically we're saying this: the delta G of reaction, which determines whether or not a reaction is spontaneous, is the chemical potential of the product minus the chemical potential of reactant, and then we've written that out as full as being the pure chemical potential plus RT log of the activity of B minus the chemical potential of A, which is the chemical potential of pure A plus this RT log of activity term. And now we can recognize that we've got two logarithm terms and two non-logarithm terms, so let's combine them. Okay, so we have the chemical potential of B minus the chemical potential of A, and we can combine those terms and say this is equal to chemical potential pure of B minus chemical potential pure of A plus RT log, and we're just going to combine these two logarithm terms. So we've got the positive term, which is activity of B, over the negative term, which is the activity of A. And so we combine these, and then we can look at this term and say, hey, that is just delta G standard, right? That's the pure stuff. That's pure products minus pure reactants. And then we look at this term, call this RT log, and we've got the activity of products over activity of reactants. We're going to give this a name. We're going to call this Q, the reaction quotient. And now we've just derived the equation that you remember from Gen Chem, that delta G is equal to delta G standard plus RT log of Q, the reaction quotient. Now we derived this for the specific case of a reaction of A going to B. We'll see on the next slide. So the more general definition of Q is defined as the product of the activities of every component in the reaction raised to the reaction stoichiometric coefficient nu. And remember that nu is positive for products and negative for reactants. So if we have a reaction, 3A goes to 2B, then Q would be equal to, well, let's see, we've got to have B to the 2, so the activity of B squared over the activity of A cubed. Of course, the coefficient for A is, since it's reactants, is -3. And so this is how we end up with products over reactants, and this is where those coefficients come from. The exponents, I didn't really explain where the exponents come from. Let's go ahead and see that on the next page. So to demonstrate where those exponents come from on the reaction quotient, let's look at this other example reaction where we have coefficients in the reaction that are different from 1. So in this case, we could say delta G for this reaction is going to be 2 times the chemical potential of B minus 3 times the chemical potential of A. Because every time you take a step forward in this reaction, every time we make take the reaction takes a step forward, we make 3 moles of B and we make 2 moles of B and we destroy 3 moles of A. So that's why we need the coefficients on here. So if we write this, we can say that this is equal to 2 times the standard chemical potential for B plus 2 times RT log of activity of B minus 3 times the standard chemical potential of A plus 3 times RT log of activity of A. And then you might remember that a property of logarithms is that if you have something before the logarithm, you can take it and put it here as an exponent. So this 3 can be moved over here, and the 2 is moved, the 2 we move from here over to here as an exponent. And that means that when we combine these, we end up with, well, first of all, we can combine these terms, the standard terms, and just call those delta G standard. So we've got delta G standard plus RT, because we're going to combine these logarithm terms. And then we have the positive term, which would be A to the second for the activity of B. And then that's going to be over the activity of A to the third. And so that's where the exponents on the reaction quotient come from. So the bottom line from all this is that delta G standard and delta G are both related through the reaction quotient Q, where Q is a product of all the activities of the products and reactants raised to their stoichiometric coefficients, and the equation that relates them is delta G for reaction is equal to delta G standard plus RT log of Q. And we have to make sure you understand the difference. It is delta G that determines whether or not a reaction is spontaneous in the forward direction. Remember, this is the slope of that reaction progress versus Gibbs energy curve, right? So if it's sloping down, the reaction goes to the right. In other words, if the slope is negative, the reaction goes to the right. And if it's positive, the reaction is going to go backwards. Okay, so it's delta G, it is not delta G standard that determines whether or not a reaction is spontaneous in the forward direction. We cannot use delta G standard to determine that unless we also know Q. We have to know the value of Q. And that's a function of all these activities, and so we can't we can't find out Q unless we know the compositions of the reaction mixture.